You should have chapter 7, section 1 for me. It's the bottom two sentences that matter to me most in this statement. This course is still eminently passable. No one is failing. Y'all are doing good enough. You might not be happy with where you are. I can't ensure your happiness. You can, because the final is still in front of us. If you have particular questions about this exam, please review the key. If you still want to know what was I looking for, what was this deduction here, come talk to me. I will happily discuss this exam with you at your discretion. Meanwhile, I want to continue talking about our recurrences. One of my goals is to figure out how to do, in general, what we did with our Tower of Hanoi problem. Now, in our Tower of Hanoi problem, we had this result. As our overall recurrence. Moving one disk took one step, and moving n disks took twice the number of steps to move n minus 1. We moved all of those to the middle peg, moved the bottom disk all the way over, and then moved those disks back to the third peg. So this applies for n bigger than or equal to 2. And we were able to show Hn was 2 to the n minus 1, I believe, when all was said and done. I was able to build that by looking at the way we processed each sequential step. But it was something special about this particular recurrence that allowed me to actually use that sort of behavior to do this. And it really comes down to the type of recurrence itself. So I want to talk about the general idea. I'm being very restrictive at the moment. I'm looking at a very small subset of the idea of a recurrence relation. All right. I got to figure out what all of this crap means. But some of these terms we've actually already used. This degree K idea. I talked about that on Friday. Okay. I'm talking about recurrence relations that look like this. What the absolute hell is going on here? Degree K means I have to go back K steps. To get AN, I need AN minus 1, N minus 2, N minus 3, N minus 4, all the way to N minus K. So our degree K idea is how far back we have to look to get the number we want. In this example up here, this is a depth 1 recursion. Our Fibonacci recurrence was depth 2. I need to go to N minus 1 and N minus 2 to get AN. I can have as deep as I want. I'm going to stick with degree 2 or lower, degree 1 or 2. But the idea generalizes degree 3, 4, 5. I might do 1 degree 3 just to show what it looks like. Now I need to understand what linear homogeneous. Wait, constant coefficient. I know. What's a constant? A number. So all of these C's, they're constants. They're elements of the real line. And this one can't be 0. If this was a 0, I wouldn't have a depth K. I'd have a depth K minus 1 or K minus 2. I need to make sure this one's not 0 to make sure I have to go back to that far. Okay? Linear. Linear? On exam 2, you had a recurrence. Grab your copy of exam 2 out of your notebook or go look on Canvas at the key. I asked you to generate the terms of a sequence with a recurrence. What was the recurrence in exam 2? Find the next, I don't know, 4 terms of the sequence that looks like exam 2. Problem number 4, Colin?
K sub n equals n times k sub n minus 1 plus n squared times k sub n minus 2.
So, not constant coefficients, depth 2. I'm still going to call this linear. Okay, now I got to ask you an algebra/calculus question, or a linear algebra question, if any of you have taken that course or are taking that course. What does it mean to be linear in a calculus sense or an algebra? The only way the variables show up is if they're weighted to the first power. In this case, the variable I'm thinking of are the AN. So here, these are all raised to the first power. There's none of them multiplied by each other. There's none squared. There's no A1 times A3. Okay. Linear in this case refers to the A's, not the coefficients. Those are still raised to the first power. That's linear. Homogeneous. This is a homogeneous recurrence. This is not. The reason this is not homogeneous is because that plus 1 on the end. Look at all of these bits over here. It's number times AN minus 1, number times AN minus 2, number times AN minus K. This is a number alone. There's no AN next to it, isn't it? Aha. So linear, because all of these things are to the first power. Homogeneous, there's nothing without an A here. Constant coefficients, non-constant coefficients. Degree K, my depth. I'm going to work with things that look like this. So something like this one. Doesn't cut it for me. On the other hand, my Fibonacci recurrence that matches all of these buttons. It's degree 2. It's linear because those are both to the first power. It's got constant coefficients because what is this Fn minus 1 multiplied by? 1. Same thing here. 1 times Fn minus 2. And there's nothing on the end here that has no F term associated to it. I'm going to give you a method that will allow you to find a solution as long as we check all 3 of these boxes. Linear, homogeneous, constant coefficients. As long as I can do all of that, I'll be able to find a way to solve this problem. What does solving it mean? Finding an expression that's not recurrence. Great. How the am I supposed to do this? Believe it or not, this entire method hinges on the idea that we made a good guess to start with. I'm going to guess based on some degree 1 ideas. I would like you to write out the first 5 values, P of 1, P of 2, P of 3, P of 4, and P of 5. What are these 5 numbers?
Beautiful. Or 3, 4, 8, 6, and 7.
And all of a sudden, my brain goes, I recognize that pattern. What should that pattern look like? P of n is 2 to the n. Very much like our Tower of Hanoi idea, I got something that's exponential in nature. So here's my guess. Things that solve recurrences of this form should look exponential. a solution to a linear homogeneous recurrence relation of degree k with constant coefficients. It should look like an exponential thingy. I don't know what exponential thingy, but it should look like an exponential thingy. So I'm going to guess it looks like r to the n for some r. I don't know what r, but it's going to be r to the n. Now, let's think about our recurrence relation. Our recurrence relation looks like this. That's the formula we said back, what, page ago? What should go on the left side if I assume that this is the right formula? Up here, this should be r to the n. What should this become? Just this piece.
R to the n over one.
And the C1 is a constant, right? I'm going to keep doing that. C2, a to the n minus 2, a sub n minus 2 is going to be r to the n minus 2. All the way down to this one, r to the n minus k. A lovely algebra trick. These all have r's in them, don't they? Let's divide by the smallest power of r. All right, I'm going to work from the right side now. This has an r to the n minus k in it. If I divide by r to the n minus k, this cancels out completely, doesn't it? And that's just going to leave me a ck here on the end. Dot, 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 click. C2, C1. I got to figure out what the right power is in these spots. If I take r to the n minus 2 and divide by r to the n minus k, what do I do when I divide powers that have the same base? Told you this was an algebra question. I subtract the powers. So I'm going to get r to the n minus 2 minus the quantity n minus k, which gives me, say again, k minus 2. What if instead of having n minus 2 here, I had n minus 1? I'd get r to the k minus 1. And then here, I'd get r to the k. This subtracting powers jazz just gave me a polynomial. I'm going to take all this crap from the right side and put it on the left side. R to the k minus C1, r to the k minus 1, minus C2, r to the k minus 2, plus minus dot, 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 minus ck, equals 0. Holy crap, wait a second. This is a polynomial in the variable r. If you don't like r, change it to x. I don't care. That's a polynomial. I know how to solve polynomials. I took algebra. I can factor. I can put them in the graphing calculators. I can put them on computers. I can solve polynomials. This, as a matter of fact, is called the characteristic polynomial. It's characteristic for my recurrence. Sometimes it's called the characteristic equation. Instead, you'll see it both ways. If I solve this for r, then I've found 90% of the solution. All right, hang on a second. I'm going to do an example. Let's start with this idea. Because if I can figure out what's going on with the example, I can figure out how to do this in general. Now, since this is a degree 2 recurrence, I have to have conditions for 0 and 1, and this rule only applies for n bigger than or equal to 2. That's what it means to be the depth of my recurrence, or degree of my recurrence. I want to go through the whole routine. Then I'm going to show you a shortcut. I'm going to do this. So I'm going to assume that my solution should be an is r to the n. This equation becomes r to the n, 5 r to the n minus 1, minus 6 r to the n minus 2. We'll worry about those later. For the moment, let's just stick with this. Move everything to one side. Divide by the lowest power. That's going to cancel this out. That's going to leave k minus 1, right? But k here is 2. So that's going to leave one of them behind. And it's going to leave two of them behind here. See how it's n minus 1 minus n plus 2? That's why I know I end up with one of them here. And if this was r to the n over r to the n minus 2, I get r to the n minus 2. The n's cancel, I get a plus 2. Shortcut. It's degree 2, your highest power is going to be 2, and they just go down from there. It's degree 3, your highest power is going to be 3. They just go down from there. Well, that's why I called it degree. This is a degree 2 polynomial. It must be degree 2 recurrence. I used the same word on purpose for a change rather than just getting the overlay. Can you solve that quadratic equation, please? There's my factoring. And that means that my two roots are 2 and 3. Those are my values of R. I don't normally switch to X, but y'all didn't like it when I wrote it in R, so I figured I'd switch to X for you. But now I have my values. Since these are the values that came from my characteristic equation, we're going to call them characteristic roots. By the way, those of you who will take or have taken linear algebra have heard this characteristic phrase before, only they say it in German in that class. Eigenvalue, same damn thing. Sorry. Wait a minute. Those are what my solution should look like. That's my recurrence, right? AN, well, is equal to 5AN minus 1 minus 6AN. This works? Really? Is that a true? Is that a true statement that 2 to the n is the same as 4 times 2 to the n minus 2? I factored out 2 powers of 2, didn't I? I'm going to factor out 1, 2 from here. What's 10 minus 6? Bing, 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 bing. It does work. So does 3. I've got to factor out 2 3s from here. That's going to be 9 times 3 to the n minus 2. I'm going to factor out 1 3 from here. So that's going to be 3 to the n minus 2. But what number goes in front of it? 15 minus 6 is 9. Son of a... Now, here's where the homogeneous part is required. If both of these work, then any combination of them will also work. A linear combination of these two things. Once I have these two basic characteristic roots, I can combine them. Multiple of the first one plus multiple of the second one, and it'll still work. And the reason that is true is because my equation was linear, and I'm making a linear combination. So I'm going to call this expression my general solution. Here's what I'm saying. But I don't want a general solution, because there are two additional pieces of information that I have yet to use. When I started this problem, what did I write down as the start of this problem? I wrote down the recurrence, and I wrote something else. What's the something else? I wrote these starting conditions, didn't I? These initial conditions are what I'm going to use to figure out A and B. To get from a general solution to a particular solution, or a specific solution. Just like when I did Calc 1 and I got the antiderivatives. If I had that extra stuff, I could solve for the plus C, right? I can solve for A and B. Now, the textbook will give you a formula for A and a formula for B in terms of the two numbers A1 and A0. And I can't remember those formulas to save my ass. So I'm going to show you the way that I think is a lot easier, because it requires something I did in pre-calculus, long time ago. A0 means n is 0. If n is 0, then I've got A0 equals 1. But this is my formula for AN. If that's AN, I get to put in n equals 0. This says A1. And that means that n is equal to 1. And that means I get to put a 1 in up here. A times 2 to the first, B times 3 to the first. Please notice this right here. This is two equations in the variables A and B. This first equation says A plus B equals 1. The second equation says 2A plus 3B is equal to 0. Back to algebra class, two equations and two variables. You know how to solve those, yes? I can do linear, you can do some matrix work. I can do elimination by addition. I can do substitution. I can do whatever I want. Solve these equations. Two equations, two variables, give me a solution. The choice of solution method is up to you. To do elimination by addition, I multiply one equation by a number so that something will cancel. I'll make it minus 3A minus 3B equals minus 3. Takes the top equation, multiplies by negative 3. Add those together, I get minus A equals minus 3, which tells me that A is 3. And if A is 3, what's B? Well, A plus B is equal to 1. 3 plus B equals 1. B equals -2. And that means that AN is 3 times 2 to the n plus -2 times 3 to the n. A, 2 to the n, B, 3 to the n. I found an explicit solution. I don't have to work this recursively anymore. You want A37, plug in 37, you're done. You want A112, plug in 112, you're done. You don't have to build all 111 that went in front of that. That's good because that would take a long time. And by the way, even I think A37 is really huge. 3 to the 37 has something like 18 digits. I'm really impressed by this idea for 2 reasons. First, it turned trying to look at this ridiculously complicated recurrence behavior into solving a bloody quadratic equation. I've been doing that for a very long time. So have you. And then the solving 2 simultaneous equations. Again, stuff you've been doing for years, literally. That changes what seemed like an incomparable problem into 2 Algebra 1 ideas. First thing I need to do is to get my characteristic equation. So what's my characteristic equation for this recurrence? I need to know the degree of this recurrence. What is the degree of this recurrence? How many steps back do I have to go? I have to go back 2. AN is in terms of AN minus 2. I have to go back 2 steps. That means I'm going to get a quadratic equation. Now, told you I'd show you the shortcut. I'm going to divide by n minus 2. How many r's am I going to end up with on the end? I'm going to end up with 0 of them. I'm going to start at r squared and work my way down. There are no r to the n minus 1s because there's no a to the n minus 1. By the way, what's r to the 0? There's the quadratic you have to solve. That ain't that difficult, is it? What are my square roots? So my general solution, these are my characteristic values. My general solution is A times the first one and B times the second one. By the way, if you switch the order and do -2 first and +2 second, that's just going to change your values of A and B with my values of A and B. Just going to swap. Perfectly fine. Gracie, you looked at that with a furrowed brow. Talk to me. We okay so far? Okay. Now I got to find A and B. This is what I believe AN should look like. This is A0. A0 is 0. Put in a 0 here, and I get A times 2 to the 0 and B times negative 2 to the 0. What equation does that render? A1 is 4. So that should be A times 2 to the first and B times negative 2 to the first. So I get 2A minus 2B is 4. Solve for A and B. But A plus B needs to be equal to 0. If I know A plus B is equal to 0, then I know that B is equal to negative A. And that gives me 2A minus 2 times minus A is equal to 4. Wait a minute, minus 2, that's 4A on this side is equal to 4. So A is equal to 1. Then I go back over here, and that tells me that B is equal to negative 1. The worst part of all of this is the freaking arithmetic. I make arithmetic and sign errors all over the place here. But that means I now know AN. AN is 1 times 2 to the n minus negative 2 to the n. When n is even, we're going to get 0. Because both of those will be positive, won't they? So this goes 0, 4, 0, 8, no, 16, 0, 64, 0, 256. It alternates between 0 and powers of 4. Questions? Oh, I want to change the Fibonacci ever so slightly. I remember I did tell you there were two versions. One was F1 was 1, F2 was 1. This gives me the same thing, but it starts with A0 being 0. So that 0 plus 1 is 1, 1 plus 1 is 2. It builds the same sequence. But I actually started at 0 this time. Problem. What's my characteristic equation? Yes, but let's go to the next step. If I divide through and I get the quadratic, I'm going to get r squared equals r plus 1. Or r squared minus r minus 1 equals 0. There's the quadratic I need to solve. It doesn't factor. As a matter of fact, the only way to solve this is with the quadratic formula. So let's do that. X is equal to negative b plus or minus the square root. Come on. You know the formula. I just have a song in my head when I do this. Bleh. So here's the problem. The problem is that that sucks. And what really sucks is that I have to plug in n equals 0 and n equals 1 to solve for a and b. Except when I plug in n equals 0, what happens? A0 is 0. When I take ugly thing to the 0th power, what do I get? 1. That equation actually works out rather nicely. It's the second one that sucks. But with a little bit of interesting algebra, this is actually solvable quite nicely. It turns out that I get a is 1 over the square root of 5. And b, because of this expression, b is equal to negative a. Which means I just came up with an amazing formula. Fn is equal to 1 over the square root of 5 times 1 plus root 5 over 2 minus 1 over root 5, 1 plus root 5, sorry, 1 minus root 5 over 2. Now, I would like you to think about this for a second. This is a formula that generates Fibonacci numbers. Fibonacci numbers are integers, always. And this formula has 4 different square roots of 5 in it. What the? It gets even worse. The quadratic equation that we solved isn't just an arbitrary quadratic equation. Somebody grab a calculator, tell me what this number is. 1 plus the square root of 5 all over 2. Tell me when you've got it. Don't start reading it yet. 1.618. That's the golden ratio, people. This is the recurrence relation for the golden ratio. That's where the Fibonacci sequence comes from. Spiral shells, ammonites, pine cones, pineapples, they're all Fibonacci numbers. This formula was produced by Binet in 1843. It's an amazing piece of work. And it always generates an integer. I have more to say about this. We'll talk about that on Friday. If you came in late, you should have homework for me and I should have an exam for you. I will see you all later.